Our next speaker is Raghu Meka from UCLA.
Thank you, Sanjay, for inviting me to the workshop, and it's great to be here at in collaboration with IFML. Today, I'll tell you about a classical problem in statistics, which is sparse linear regression, and we'll be talking mostly about what's the computational efficiency we need for solving this problem. And this is based on joint work with Jonathan Kelner, Frederic Koehler, and Dhruv. So the problem we're going to study is a basic regression problem. So you have access to samples from a distribution x comma y. X are your covariates, which are kind of, maybe the simplest non-ideal distribution, which is a standard multivariate Gaussian. Okay. So we'll call X a covariance. You have a covariation, you have a covariance matrix sigma, which can be arbitrary. And the response variable Y is determined by a sparse signal W star. So for each example X, you compute its inner product with your unknown signal W star and add some noise, and that's your response variable. And our goal is to recover, or at least approximately recover W star, depending on how much noise you have and whether or not even there's noise. The goal is to get small prediction error in small prediction error in the right metric, in the sigma metric. Okay, it's a simple and basic statistical model. And for simplicity, in the rest of the talk, I'll focus on the case where there is no noise and we're looking to recover the W star exactly. Our upper ones will actually generalize to the noisy setting too without much change. But let me focus on this to highlight the main ideas. So as classical as this problem is, there is still an exponential gap in what is possible information theoretically and for what is possible computational efficiently. So we can show that for any non-singular sigma, we can actually recover W star with only klogn samples. This applies to no matter what sigma is, as long as it's non-singular. What do we know in terms of efficient algorithms? For arbitrary sigma, we don't have anything which runs in less than brute force time, meaning you're enumerating all possible k-sparse signals, meaning you can't get runtime n to the little of k with less than linear or sublinear number of samples. If you have linear number of samples, it just becomes standard linear regression. You don't care about sparsity, everything is fine. But once I have some sparsity, we cannot beat, or at least we don't know how to do it with something which is little of n. The main challenge is, what is the computational limit? At what point can we get non-brute force algorithms? There's a lot of work on this problem, especially in the context of computer sensing and related questions. So one of the most studied techniques for solving this problem is the L1 minimization method, or Lasso, where you just try to find a solution to the system of equations x times w equals y, but you try to find a solution which minimizes the L1 norm. So typically, we know that these methods work if the covariance matrix, for instance, is identity matrix, meaning everything is independent, or the covariance matrix is well conditioned. Meaning typical guarantees, again, this is all in quotes because there are lots of different versions, different optimizations, but typically it's something like this. If the condition number of a matrix sigma is capital T, then you get some sample complexity, which is k times t times log n. And your runtime is going to be very efficient, polynomial time for sure, and even better in some cases. Okay, but the dependence on t is what is not there in the information theoretic bound. And that's what we're focusing on. And what do you know in terms of computational barriers? We know that this regression problem is hard in the worst case. Meaning, if I give you a fixed set of samples, x1 through xm, it's a fixed matrix, then there are hard instances. You can embed pretty much set cover or independent set without too much difficulty. And for specific algorithms such as Lasso, we do know that there are covariances which make Lasso fail. There are some sigma where Lasso would not work with klogn sample complexity. But even though it makes Lasso fail, if you just do a simple basis change, it starts working again. Again, that's something we're going to talk about in a little bit.
In the worst case hardness result, is the sample complexity depends linearly on the condition number, or could you go for root t or something? Or
It's a pretty kind of very strong lower bound. It basically says that as long as you have like over 10 samples, you're going to need almost exponential number of exponential runtime, assuming some other hardness. Basically, you can reduce from something like clique.
Okay, but the precise dependence on the condition number is not clear.
Yeah, maybe root t. I would say. I'm saying like basically it's hard to decipher what the dependence on t would be from the construction because t kind of appears both in terms of the number of variables and something else. Okay, so it's not immediate.
Okay. Kind of relates to this question. How are these matrices? Like, what is sigma for those matrices that make Lasso?
So there is no sigma there. It's just a fixed matrix, meaning I have x1 through xn. So it's a fixed design matrix.
Okay.
So it's not really you don't have a distribution for which we know it is hard. I mean, you can say it's a distribution with finite support.
Sure.
But that's about the only thing.
And how do they make these matrices?
So you take an instance of set cover as an example, and the sets will correspond to the rows, and you have to do some maybe a couple of tricks on top, but that's something like that. Okay, that's kind of the first sort of significant bit, and then different variations give you nice trade-offs. Okay. All right. So the main questions then are: can you bridge this exponential gap? And you can work on trying to bridge it from both ends, right? So on one end, you can ask, can I go beyond worst case? We know we don't have very strong algorithms for worst case instances of sigma now, just a covariance matrix. Are there interesting special classes of covariances where we can get efficient algorithms? And well-conditioned we know is enough for actually designing algorithms, but it somehow doesn't capture many other interesting regression problems. As we'll see, there are natural instances where the condition number is terrible, and in fact, these methods will fail. And on the other hand, you can ask, okay, are there classes of algorithms that we know will fail for this random instances? Meaning there's a fixed sigma, but it's an average case lower bound because the input to your algorithm is randomized. Okay. Can we get worst? Maybe can you show this is hard for some class of algorithms, as we'll see later on.
But again, when you say worst case hardness, not enough, you mean worst case hardness, the fixed design setting.
Yeah, in the fixed design setting.
So, but that's a
oh, I see.
That's a totally different thing. Like there, you're not assuming Gaussianity or
yeah, exactly. So that's the only hardness we know. So it's much poorer. You're right. I should emphasize there's two different worst cases.
In your talk today, everything is Gaussian and they have nothing. I think variance and like everything is over.
Everything is over. There's an exponential gap for that. Okay, and we'll see an example of making progress on the beyond worst case setting. We'll look at various covariances which are ill-conditioned, but if they have some specific graphical structure, I'll define what it is, then you can solve it in almost optimal sample complexity. Again, definitely the dependence on n is going to be logarithmic or polylogarithmic. And the main technique we use for solving this, which is preconditioning the Lasso method, we show has limitations, even though it works for this graphical structure. You can show that there are covariance matrices which cannot be preconditioned so that Lasso would work. Okay, even if you know the sigma, you cannot design a precondition even based on sigma. But I'll get more precise as we go along. Okay. So first, let me talk about the upper bound, which is how do I precondition to solve some ill-conditioned SLR instances. And I'll use this random walk as a motivating example to both describe the problem and also describe the algorithm, and then we'll generalize it without too much difficulty. So what's a random walk covariance matrix? So here you should think of RS as Xi just for the random walk setting. So you have n random variables as before, they're all Gaussian, but they're being generated as follows. I have IID Gaussians Z1 through Zn, which are kind of latent. And the ith variable that you actually see as covariate is your I-1th variable plus this independent Gaussian Zi. Okay. So the ith variable is just the sum of the prefix of the Z's up to I. The covariance matrix of this is exactly, if you just squint at it a little, the correlations are exactly this. The covariance matrix is very simple and nice. It has kind of almost the same nice pattern. But if you focus on the diagonal, you can see that the ratio of the entries of the matrix changes or increases with the dimension. Okay. So this covariance matrix is actually very badly conditioned. Is ill conditioned. The condition number depends on the dimension n. And this is kind of, you can think, maybe not this exact equation, but this sort of dependency structure can arise in the real world. For example, if you have time series data where your next variable only depends on the previous one, or maybe a few before that, then you might get such a setting. Okay. And as I said, it's ill conditioned. And so algorithmic guarantees that we know longer apply. All right. And it's not just that they no longer apply in analysis, they actually fail when you implement them. So if you take Lasso or BP or any other methods, on a case where the dimension is large, like 32,000, but the sparsity is 2. Okay. So it should be something like 2 log n information theoretically, but you see that the existing methods need a lot of samples to work. In particular, it seems to be almost linear in n. But there is one outlier here, the black curve, which is going to be a preconditioned method, which solves this problem, even with the almost right sample complexity. Yeah.
You say k log n, and I'm always thinking of k log n over k. So I'm thinking, you're thinking k is constant or something?
K is small.
K is constant.
Yeah. Not constant, maybe.
Okay, because if k is constant, I can do polynomial time.
Right, but it depends. Like that's what I want to say. Like if k is 100, n to the 100 runtime is not good for me.
All right, so you don't want to think k is constant.
Yeah. Okay. Or you can say, okay, I want k is like 1000, but I want my runtime to be like n squared n, which shouldn't, the exponent should not depend on k. Right, but it's best to think of k as being like logarithmic or something non-constant, then makes a lot of sense. So the technique that we're going to study is preconditioning. So preconditioning is something that gets widely used in numerical linear algebra and solving linear systems, and also in many other optimization algorithms. And here we're going to try and use it for improving the sample complexity, not for kind of the runtime, but for the sample complexity. So what is preconditioned basis pursuit or preconditioned lasso? Instead of, you're still looking to solve x times w equals y, but instead of minimizing the L1 norm of w by itself, you try to minimize the L1 norm after some basis change. Okay. So if S, the preconditioning matrix is invertible, this essentially corresponds to making the transformation S inverse X. You have your original X, you make it S inverse X, and then you're running Lasso. Okay. Both are equivalent. So if you're trying to use preconditioning, the idea is, maybe your original set of random variables, x1 through xn, their condition number is bad. I'm going to do a basis change to make the condition number very good, and then I'll use Lasso. That's the simple thing to try, simplest thing to probably try. And let's try and do this for random variables r1 through rn for the random walk. Right? So you want to transform them into w1 through wn. Maybe the first thing you would try is, because I want good condition number, right? Somehow I want independence. The first thing to try is to take the differences, right? So I define my new variables wi as ri minus 1, then I'm golden, because we know that the differences are all independent standard Gaussians. So the good here is that we got the covariance to be perfect, its identity. So it's extremely well conditioned. Okay, so if you were to, you could have used the Lasso guarantees from earlier. But the problem, the ugly part, is that we lost the sparsity of the signal. What do I mean? Suppose the response variable y was just R1000. So it's a one sparse linear combination of your input covariates, R1 through Rn, right? But under this basis change, in the new basis, the response variable becomes the sum of the first 1000 variables. Okay, so you lost sparsity, so the Lasso guarantees do not apply. Right? So the simple thing, first thing to try doesn't work, mainly because we want this transformation to not only make the condition number better, but also to go back with sparse combination. Meaning we want each Ri to also be a sparse combination of our new variables Wi. If we have these two, then this would work. Basically, you improve the condition number, you don't blow up the sparsity too much. So that's our revised goal. We have a better understanding of why it's necessary. And the trick to do that is a simple geometric one. The idea is to exploit the nice Markovian structure of the random walk. So what do I mean? If I take the middle vertex, the RT over 2th variable, then everything to the left of it, the first half minus 1 variables, become independent of the right half minus 1 variables. Once I condition on the middle one, the left and right become independent. More generally, if I condition on the ith variable, the left and right pieces, Ri plus 1 through Rn, as a set become independent of R1 to Rn minus 1. Okay. Independence is good because even the condition variables will be Gaussian random variables. And if they're independent, then their inner product is 0. So the covariance becomes very nice. Okay. So the idea is to do this recursively. So let's say I have 7 variables, this xi's. I take the middle vertex x4 and condition it out, meaning I'm replacing each of the other ones in some kind of by a shift of x4 so that the inner products become 0. Okay. For each one, I subtract the right multiple of x4. That splits out the left and right halves. They become independent. And now you recur. So you have 2 separate problems, so you do it again. You have to do a little bit of arithmetic to figure out these combinations, but once you have this idea, you can work it out without too much difficulty. Okay. And if you do this for this special case of 7 variables, this is the picture you get. And by the Markov property, you can argue that all of these variables, the new variables that you have here, you just did a linear transformation of your original inputs. They're all independent of each other now. You can check by just taking the inner products, they'll exactly cancel out and give you independence. Okay. So we got nice condition number now. The other thing to check is, are we preserving sparsity? What do you think? The sparsity is also fine because it depends on the depth of the tree. So because you can write each of the old variables as something along this path, as a path in this binary tree. So you can do it with exactly log n loss in sparsity. So every old variable is a sum of log n new variables. For instance, x1, you can write it as basically trace the path along to the leaf corresponding to x1. Right? So that's our desired basis change. We kind of got to this in this intuitive way. Yeah.
Sorry, I don't understand the construction. Can you explain what is independent?
So basically, imagine, so there is a way to come up with these coefficients, okay, based on this recursion idea. But suppose I had these original variables x1 through x7. Now I did a transformation where I'm replacing x1 with like x1 minus half x2, and all of this other stuff. So this is a linear transformation of this. And the point now is that each of these new variables, they're all independent of each other. So I have a new n-variate distribution.
Like all 7 choose 2 are independent.
Yeah, exactly. Because it's Gaussian, once their inner product becomes 0, they become independent. Okay.
How much does this rely on Gaussian?
It relies on Gaussianity. The independence you can still ensure by Markovian property. But Gaussianity really comes from the fact that the conditional distributions are linear shifts. So it uses Gaussianity reasonably strongly.
So if I have a covariate matrix whose distribution is sub-Gaussian, then this
it might not work with this simple idea, but at least maybe there's some variant of this splitting of the graph. That
so actually it will work in some sense and not in some sense. So like the Markov property may not, like in Gaussian, the best predictor of one thing, everything else is linear. So that's kind of like if you think about graphical models, that's why Gaussian is important, which is what Raghu is saying. But on the other hand, if you just have the covariance matrix and invert it, and this matrix has this graphical structure, there's kind of like independence would only look at linear functions, and it works actually under much weaker distribution.
So for Gaussian distributions, it's easy to understand what the dependency graph is. For sub-Gaussians, it's not like, if I just tell you the covariance, you don't know what the dependency graph is. So if you know that the dependency graph is of this form, then and some conditions, you can do it even for sub-Gaussian or even sub-exponential distributions. It depends on the dependency graph.
I don't see independence. X1 minus half X2 and then X7 minus X6. Suppose I take these two end leaves. Then when I multiply them, I don't see any terms canceling. So what do you mean by independence?
Well, okay.
I'm missing something.
I'm sure Freddie or Dhruv did this calculation right, but if you take the inner product, maybe you can check, right? Now, what's the inner product of 1 and 7? It's 1. 1 and 6 is 1, so it gets canceled, right? And half of X2 is inner product with X7 is 2. You get 2 minus 2, you get 0.
Okay.
Okay, so you're getting cancellation.
Okay, now I get it. Thanks.
But you can check manually, but the way you're doing it really is one step at a time. So you ensure kind of the left half and the right half, you satisfy it once, and then inductively you satisfy it again and again. Yeah, I mean, if you check, like basically the correlation of X1 with X7 and X6 and X7 is the same.
Yes.
So when you take the difference, it goes away.
Got it.
Yeah.
Just to be sure. So XI is your design linear regression.
Yeah, those.
And this works only for this particular design when you have this recursive formula when you add.
Yeah. Right.
So for this particular design,
Exactly.
it's not like.
So this basis change is also has a name and history. It's actually the Haar wavelet basis. Okay, so you can also just say, okay, we're doing the Haar wavelet basis, but thinking about it this way will help us generalize a bit more, as we'll see. Okay. As a corollary, you basically get that when the covariance matrix is from the random walk. So let's say you're trying to do regression on time series data. The coefficient, as I said, they're not important. What's important is the Markov property. Then preconditioned BP, you can solve that problem with basically k log squared n samples. Okay. And random walk is kind of, in our argument itself, you can see that you're not really using too much about the coefficients or the walk. So there's a more general thing that we can extract. Yeah.
You because of the transformation, your sparsity got a log n factor, and
Exactly.
that's why
there's a log squared. Exactly.
Question. So what is the preconditioning here? So the first preconditioning you had was simply sigma inverse and then K sparsity.
Right.
With this construction, what is the preconditioning?
So the preconditioning is basically whatever transformation you're doing, right? Okay. So you're kind of describing S inverse in some sense. You do this transformation and then you're solving L1 just in this space.
Let's make sure. Also, you need to control the coefficients.
You need to control the coefficients, but the coefficients will not be too big either.
So in general, going beyond the random walk, how is this preconditioner going to look?
Yeah, I'll tell you that in a second. So to abstract it out, let's first look at the main property of random walk that we're using, which is the following Markov property. So for any graph, for any this set of variables x1 to xn, you can define a dependency graph. We say G is a dependency graph if whenever you have two vertices that are not adjacent in this graph, then they're independent conditioned on neighbors of one vertex. Okay. So meaning, so for instance, for example, for the random walk, it corresponds to the path being a dependency graph. Because if I take any two variables, then conditioning on neighbors of one vertex, meaning I'm conditioning on, let's say, at least one next to it, then the two variables become independent. Okay. So more generally, you're saying, I might have an arbitrary graph, not necessarily a path. You could have a grid graph, you could have all kinds of graphs that show up. Okay. And for Gaussian distributions, there's a nice way to get to dependency graphs, and that comes in the precision matrix. So it is well known from, I think, the 70s that if I take covariance matrix and look at its inverse, that's the precision matrix, its non-zero entries tell you exactly the dependency graph of the distribution. Okay. And this dependency graph, this class of models are also called Gaussian graphical models, and learning them and using them has been studied a lot on its own. But today we're just going to use them for as an assumption so that we can solve sparse linear regression. Okay. All right. So we're going to assume that the dependency graph of the distribution has small treewidth, 5 minutes, right? And So why is tree width a nice concept? If you don't know what tree width is, the main thing to keep in mind is the following property of tree width. You see, Satish has walked in exactly when I'm talking about tree width. Somewhere the bells rang. Okay, so you have the balanced separator theorem. So this is the main property of the dependency graph that we're going to use. That if the tree width is t, then you can partition the graph into two smaller pieces by taking out only a small number of vertices. So the tree width is t, there are constant times t many vertices that you can find, such that if I cut them, if I remove them from the graph, then the graph partitions into two pieces where no piece is bigger than 2/3. So you're getting a constant fraction drop by only removing a constant number depending on t many vertices. Okay. So now we have this. What should I do to get my preconditioner? In sessions, well, you do the same recursive thing, right? You kind of take out the vertices in the middle. Let's call the set A. So you identify the vertices in A. You orthogonalize everything else with respect to these variables. Again, I'm saying orthogonalize because it's basically just like doing some kind of Gram-Schmidt process with these vectors to begin with. Some simple algebra there. And then you recurse on the left and right pieces. The intuition is the same. These set of variables and this set of variables are now completely independent of each other. So what do you do there? What you do here doesn't affect the covariance matrix in the end. And because the sizes of these left and right pieces is always dropping by at least a constant factor, your process will stop within log n depth. And in each step, you're taking out t vertices. So the size of this cut in the end, you're trying to increase, you'll increase the sparsity by something like t times log n.
So how quickly can you like decide a tree width, like approximately?
So we need to know the graph for sure. I'll talk about that in a second. And I mean, I don't know the best one, but we're just not, we're assuming it's kind of known in some instance. Actually, that's a good point. We don't need to find like, we only need an approximation. Like a constant factor approximation is good enough for us because all we need is this geometric decay. And I think if once you have a tree width, it's also easy to find separator and so on. Okay. And this, I mean, as I said, some of these preconditioning techniques have a long history in numerical linear algebra. This is very close to something called nested dissection techniques for solving linear systems, which was done way back in the 70s. Okay. So in summary, what you get is that if the dependency graph has tree width t, then you can solve it preconditioned belief propagation or basis pursuit or any of these things. Once you do the basis change, we'll solve sparse linear regression, and the number of samples is going to be k times t times log squared. Okay, so for constant tree width, you're doing really well. And constant tree width models are relatively common. They arise, for instance, in linear dynamical systems, autoregressive models, where let's say you have time series data, for example, and you say, okay, the next variable only depends on my past 10 events, and then there's some randomness. Those are also called structural causal models. So in all of those things, you might get something like this. Okay. So let me now, in the remaining 2 minutes, tell you a statement of our lower bound. So we saw that if the dependency graph has small tree width, then we can do it without assuming anything to do with the condition number. And actually, I should say that we don't need to know the covariance matrix for upper bound. We need to only know the dependency graph. Okay, sometimes the dependency graph is something that you can, from prior knowledge. Maybe the exact coefficients that you have, it might be a hard problem to learn. What about other dependency structures? Suppose you have variables which are kind of being generated on a grid. Right, so grid has this annoying property that it is tree width is very large. Okay, so what do you do in this case? Our method, as I stated, doesn't work. The grid graph, the dependency graph is very sparse, seems very nice, but the tree width is omega root n. Okay. And what we show is that, unfortunately, there's some kind of tree width is a bottleneck, high tree width is a bottleneck for preconditioning as a whole. Meaning, for any graph which has tree width t, there is some covariance matrix that you can put whose dependency graph is exactly that graph. And any preconditioning that you can think of, it can depend on the graph, it can depend on sigma, would still require t to the 1/20 samples. Okay. So the emphasis is basically on the fact that the preconditioning can depend on sigma or anything, but still you'll get this lower bound. And if you don't, I mean, even if you don't focus on treewidth, it's independently interesting. Basically, you're saying that there are covariance matrices, sigma, for which even if the sparse signal has sparsity like logn, any preconditioned lasso will require a polynomial number of samples, okay, n to the omega 1. And this is for such lower bound. For a broad class of algorithms, broad here corresponds to any possible preconditioner you can use. Okay.
And preconditioning means only linear transformations.
Yeah, only linear transformation. Yeah. But you know, the transformation can depend on your sigma.
Right. But there could be some other transformation, or there could be another convex program that.
Yeah. So after doing the transformation, you could ask, you know, maybe instead of L1 norm, I do something else. But although, you know, I think you might be able to handle that. But the main thing is a linear transformation. So the high-level proof sketch is, in the interest of time, I won't say what it is, but basically it involves some gadgets and it's a more complicated part of the paper. It takes a lot of effort to kind of get it on a grid. And let me finish with basically what are the next steps possible. First, we don't know how, I mean, our thing fails when you have high treewidth, and there's a good reason it fails. That preconditioning as a whole won't work. And you can ask what happens, you know, maybe can I do it on grid graph? Or what if the distribution has some kind of sparse factorization, the covariance matrix has sparse factorization? And more generally, I like this theme of using structural assumptions on your covariance matrix, especially on, like, let's say by Markov property or something nice about the dependency graph, to go beyond worst case. I think that's something that could be useful for other regression problems as well. Okay. So let me end with that. Yeah.
So you mentioned that you don't need to know sigma, you only need to know the graphical structure. But then in the Gram-Schmidt process, you had that xi, xj.
You can do it with empirical things.
Ah.
Because, you know, the sparsity is small enough that you don't need to do it fully. It requires a bit of care to kind of make sure the errors are not blowing up and so on, but you can do it.
Thank you, sir.
Thank you very much for nice talk. Actually, I am confused about this procedural algorithm. So usually we want Lasso to make some feature selection. We expect some sparse end of the day. But here you are just with sparsity in a different space.
Right. So basically, it might be true that your signal is sparse in a different space. Can you somehow automatically find it?
So how you understand some solutions that are not sparse in the original space, they're sparse somewhere else. So we cannot do any more feature selection, right?
I think the map is, or like at least the one we use for the algorithm is sparse
In both directions.
So once you do feature selection in the other space, you can't go back.
Why does sparse? So you take the matrix, multiply by the sparse vector.
Yeah, so like
But matrix is not sparse on anything.
yeah, once you get the features in the preconditioned space, you can go back and find like log n factor more features in the original space.
So basically, the transformation is sparse on both ends. Like, you know, the way we are doing it, the transformation, the new features are also sparse in the old feature. Okay, so you have your original set of variables.
Right? So you take a sparse vector, you multiply by a matrix. What is the structure of this matrix? It's a double linear combinations of xi, but the xi are not sparse, right? It's just full matrices, Gaussian matrices.
You get sparsity here. So the new variables wi that you have are sparse combinations of the old ones.
Yeah. In the interest of time, let me do that.
Yeah.
Thank you very much.